let's find out how we can calculate the correlation of a given pair of random variables x and y. And recall that random variables can be used to represent and contain data from samples or from population. So in this case, we need to be clear or we need to seek from the question, what do the variables, the random variables x and y represent? Do they represent population? Then we need to calculate the population correlation. If they represent samples, then we need to calculate the sample correlation. So let's say we are given a set of samples. There are 10 of them, but 10 pairs of measurements x and y. So it's pretty much the same data as we saw in our covariance example just now, and intentionally so, because as we see in the definition of correlation, it is defined in terms of covariance. All right, so we have sample correlation is the sample covariance divided by the sample standard deviation of x and the sample standard deviation of y. So we all know how to use calculator, Excel, and R, and Python, and other programming languages to calculate quite easily the standard deviation of a set of data. And recall from our practice example just now, we are able to calculate the sample covariance of given set of explicitly listed data, right? So they are explicitly listed in the sense that duplicate pairs like 9797 are allowed, right? So 9696, if it so happens that the pair of measurements repeat, then they repeat, right? So let's flip back a few slides to look at our covariance, sample covariance of x and y calculations based on the same um, set of data here. So what we did was just to apply the formulas, and we have to first calculate the x bar and the y bar, and we did that, and then we do the substitutions, and then we are able to arrive at the sample covariance. And if we treat the two sets of measurements as population, then we apply basically the same calculation but divided by n, where n is 10 rather than n minus 1. So in this case, then we get minus 0.1. So that will be treating the set of data as population. So we calculate population covariance, and that's minus 0.1. And if we treat this as a sample, meaning there are a lot more measurements that our sample hasn't captured, right? So in that case, we calculate the sample covariance, and it turns out that it is negative 0.1111, so a bit larger in magnitude. So let's turn back to our correlation calculation. So from calculator or otherwise, we can calculate the sample standard deviation of x. That's 0.5164. And you should verify that. And also the sample standard deviation of y, and that's 0.5270. And let me know if that's not correct. I believe it is correct. So from our covariance, sample covariance calculation, we plug that result here and then divide up, we'll get negative 0.4082. So that's sample correlation. And that's having a negative sign. We'll talk about how to interpret the number, the correlation value in a moment. But right now we want to focus on getting the calculation right, because that's where you score marks, and that's where we get our correct descriptive, correct summary of this huge set of data into a kind of a easy to interpret number for us to make decisions. So if we treat the entire set of data as the whole population, so this is it, right? So this is all the measurements in the universe that we care about, then we have to calculate the population correlation, and that's represented by rho, and we'll just use the population versions of the numerator and denominator. So recall just now that our population covariance, if we treat the data as population, was negative 0.1, right? So that's where we use it. And we will calculate, or actually recalculate this using treating it as population. And so the population standard deviation will be 0.4899. And likewise, the population standard deviation of y, the numbers don't change, but because the formula for the population standard deviation and the sample standard deviation, they are somewhat slightly different, right? Just like the difference between sample covariance and population covariance. So that's why even though the numbers, the data don't change, the resulting population standard deviation of y has gone from 0.5270 to 0.5. So once you divide, you get this very strange number, negative 0.4083. Now, two things are happening here. Number one, this 3 actually should have been 2 had it not been due to the rounding off to 4 decimal places in all these calculations. So if in a perfectly precise world, we would get exactly the same number, same sign and magnitude for R and rho. All right, so that's supposed to be the same number. So this 3 here is just due to rounding, and in all honesty, we just show it here. But we should know that treating the set of data here as sample or as population will result in the same correlation values, not the same covariance values. Notice that? Okay, so that's point number one. Point number two is that, strangely, even though if we treat the same set of data set as sample and as population, the sample covariance and the population covariance differ, right? Even though they differ, the sample correlation and the population correlation for the same set of data is exactly numerically the same. So this sameness of the values is deserving of a bit of understanding here, all right? So what is happening here is not because the numbers here are specially chosen to make this happen, but that this is true in all cases, no matter how many data sets you put in or how the numbers change. So you can think of it as the fact that dividing by the standard deviation of x and y, well, sample or population using the right version, is standardizing the fluctuations of covariance in such a way that when covariance is, of a very large value, the standard deviation value will also be large enough to kind of tame it down. You can think of it that way. So we're just talking figuratively, right? So as to gain a bit of understanding as to why the numbers are like that. And so when the covariance value is small, all right, then the standard deviation, whether sample or the population, will correspondingly be small enough to make sure that they vary in the same way, so as to, after division, cancel off the effects. So they cancel off in just exactly the right way all the time, that whether you calculate the sample correlation or the population correlation, you find that they are the same numbers. Okay, so having said that, numbers are the same, but the context is entirely different. In other words, even though we have now been assured that whether you kind of sloppily carried out using the sample correlation formula or the population correlation formula, either way you get back the same answer, isn't it? On the left-hand side, you cannot be sloppy. All right, so if you intend to treat this data set as sample, then you need to use R, because it should be sample correlation. And otherwise, if you treat it as population, then you should write rho, because the meaning is that when rho equals to negative 0.4083, it implies that that's it. I'm looking at the whole universe. There's nothing else that I haven't seen. However, if you write R equals to negative 0.4082 as the correlation value, you're saying that, well, this is just a random subset and there are possibly a lot more values that I haven't seen, so be a bit cautious in your interpretation. Okay. Now, don't find it strange because if a person is called Tony and another person is called Tony, you don't say that these two people behave the same way. They come from the same country. They eat the same food. They wear the same dress or clothes. You don't do that, right? You instinctively know that you are what Tony Lim. You are Tony Edward or something like that, right? So you inherently want to find some properties to distinguish the two because you know they are not. Having been called Tony doesn't mean they are of the same person. So likewise, having the same numerical values all the time for any data set doesn't mean that on the left side they represent the same context. So you need to be super careful about that. Okay, so I just want to point out the sameness part, and that is the source of um, carelessness because one might think that they are the same, so left hand side doesn't matter, but it matters a lot. So pay careful attention on whether you are supposed to write R or supposed to write rho. Yeah? Next, on calculating the correlation of a given probability distribution. So, and because correlation involves two random variables, it most likely will come in a form of a table like this, which we have seen when we calculate using covariance on distributions. So not surprisingly, we are going to again invoke the use of covariance divided by the standard deviation, right? Population covariance in the sense, so sigma xy. And because it is distribution, there's no what you call it, no fear of having the ambiguity of the author trying to mean sample or population. It will always be population, yeah, because the frequencies or the fractional frequencies or the probabilities here add up to 1. So that means 100%. So we will always be focusing on just the population correlation when we are given a distribution. So if the question should ask, calculate the correlation of the following distribution, and they give you a table like this, you don't need to feel stuck, right? Question is not clear. Are you trying to ask for sample correlation or population correlation? It always will be population correlation. So how do we calculate it? Very simple. We of course need the population covariance, and to do that we need to calculate the population mean of X, population mean of Y, and we have seen that before. And then we do the necessary to find that the population covariance is negative 0.1. And then we calculate the population standard deviation. That's the big square root of the square of the difference from the mean of X, right, of each value, 8 and 9, times its own probability. Yeah, so 8 and 9, 0.1 plus 0.3, 0.4 plus 0.2, so to get 0.6. So we do that, right? You can use calculator or otherwise. So you get these numbers, and then you divide up, you get the population correlation, which is exactly what we have seen earlier on here. Yeah, because this set of data, right, the amount of duplications, they are reflected in exactly the same proportion here. Yeah, so that's it. That's not surprising that we get back the same population correlation. Okay, so that's easy, so long as we can calculate the population covariance, and that is also not difficult because we understand the motivation and the visual implication of this calculation.